During CPB, a perfusionist notes a sudden, unexplained drop in venous return accompanied by chattering of the venous line. What is the immediate pathophysiological cause? A. The arterial line filter is completely clogged. B. The venous cannula is too large for the patient's vena cava. C. The venous walls are collapsing against the cannula due to excessive negative pressure or hypovolemia. D. The oxygenator is experiencing a water-to-blood leak. Answer: C. The venous walls are collapsing against the cannula due to excessive negative pressure or hypovolemia. Explanation: venous chattering occurs when the kinetic or gravitational pull on the venous line exceeds the available blood volume in the vena cava. The negative pressure pulls the flexible vessel wall directly against the cannula ports, momentarily shutting off flow. The flow stops, pressure builds up, the vessel releases, and the cycle repeats rapidly, causing the line to visibly shake or chatter. It is resolved by reducing vacuum, partially clamping the venous line, or adding volume. If the arterial roller pump head is under-occluded during the pre-flight safety check, what is the consequence during actual cardiopulmonary bypass? A. The pump will deliver less forward blood flow than the digital readout calculates. B. The line pressure will dangerously exceed safety limits. C. Severe spallation of the inner PVC tubing will occur within minutes. D. The patient's blood will become rapidly hyperoxygenated. Answer: A. The pump will deliver less forward blood flow than the digital readout calculates. Explanation: roller pumps rely on precise occlusion to displace a known volume of fluid per revolution. If the rollers are under-occluded, not pressing tightly enough against the backstop, a portion of the blood will slip backward past the roller head whenever it encounters resistance, after load. As a result, the actual forward flow delivered to the patient will be significantly lower than what the pump's revolutions per minute, RPM, calculator displays on the console. What safety hazard is directly associated with the use of an inline hemoconcentrator, ultrafilter, left running on a low blood flow rate for an extended period? A. Hyperkalemia due to massive red blood cell destruction. B. Hemoconcentrator thrombosis and potential systemic embolization. C. Catastrophic drop in systemic vascular resistance. D. Massive air entry through the semi-permeable fibers. Answer: B. Hemoconcentrator thrombosis and potential systemic embolization. Explanation: hemoconcentrators divert a side stream of blood through ultrafiltration fibers to remove plasma water. Because they concentrate cellular components and clotting factors within their housings, maintaining a robust blood flow rate is essential. If the flow drops too low, stasis occurs, significantly increasing the risk of localized clot formation inside the filter, which can compromise the device or shed thromboembolus back into circuit. Which mechanical safety backup device is designed to automatically redirect blood flow around a totally occluded arterial line filter without interrupting systemic perfusion? A. The recirculation line. B. The filter bypass loop. C. The purge line. D. The cardiotomy isolation valve. Answer: B. The filter bypass loop. Explanation: in the event that an arterial line filter becomes completely obstructed by microaggregates or clot formations, a dedicated bypass loop, a parallel line with a series of stopcocks or clamps, allows the perfusionist to immediately shunt blood flow around the blocked filter and directly into the patient's arterial cannula. This preserves life-sustaining systemic perfusion while troubleshooting or replacing the faulty filter. During CPB setup, why is it critical to ensure that the cardioplegia vent/purge line remains open or functional during administration? A. To deliver anesthetic gases to the myocardium. B. To vent out any accidental air bubbles introduced during the mixing of cardioplegia solutions before they reach the coronary arteries. C. To measure the systemic blood pressure of the patient. D. To cool down the lung parenchyma. Answer: B. To vent out any accidental air bubbles introduced during the mixing of cardioplegia solutions before they reach the coronary arteries. Explanation: coronary air embolisms during cardioplegia delivery can cause profound, irreversible myocardial ischemia or right ventricular dysfunction once the heart is restarted. The cardioplegia delivery system utilizes a localized vent or purge line at its high point to continually escape any air bubbles generated during the formulation or switching of cardioplegia doses, ensuring only bubble-free solution enters the coronary ostia. What is the dangerous physiological consequence of an accidental nitrogen or room air flush into the gas phase of a membrane oxygenator while blood flow is completely static? A. The blood will instantly freeze. B. The oxygenator will lose its structural rigidity. C. Nitrogen or air will rapidly cross the micropores, causing massive gaseous embolization within the stagnant blood columns. D. The pH of the blood will abruptly swing to a critical alkaline level. Answer: C. Nitrogen or air will rapidly cross the micropores, causing massive gaseous embolization within the stagnant blood columns. Explanation: just as with an active oxygen sweep, running any dry gas, like room air or nitrogen, through an oxygenator when the blood phase is stagnant creates a severe gas-to-liquid pressure gradient. Gas will readily traverse the hydrophobic microporous fibers into the unmoving blood. When pump flow is resumed, this massive column of micro and macro bubbles will be swept directly into the patient's arterial tree. Why must hardshell cardiotomy/venous reservoirs always remain adequately vented to the atmosphere during standard gravity-driven CPB? A. To allow carbon dioxide to escape the room. B. To prevent the buildup of positive or negative pressure that could impede venous drainage or cause reservoir structural failure. C. To allow the perfusionist to smell the blood for hemolysis. D. To keep the priming fluid at room temperature. Answer: B. To prevent the buildup of positive or negative pressure that could impede venous drainage or cause reservoir structural failure. Explanation: in an open hardshell system, air is constantly displaced as blood enters or exits. If the atmospheric vent is clamped or blocked, incoming blood or gas lines will build positive pressure, slowing or stopping venous return and potentially forcing air retrograde. Conversely, pulling blood out of an unvented rigid container creates a vacuum that can crack the housing or draw air from surrounding lines. Which parameter measured by an inline circuit monitor is the most sensitive early indicator of inadequate systemic oxygen delivery, due to, during hypothermic CPB? A. Arterial line pressure. B. Venous oxygen saturation, SVO2. C. Pre-filtered transmembrane pressure. D. Sweep gas flow rate. Answer: B. Venous oxygen saturation, SVO2. Explanation: venous oxygen saturation, SVO2, measured continuously in the main venous return line, reflects the balance between systemic oxygen delivery, due to, and systemic oxygen consumption, VO2. If the pump flow is too low, the hematocrit is insufficient, or the patient's metabolic demand spikes, tissues will extract more oxygen from the available blood, causing the SVO2 to drop below its target range, typically 70 to 80%. While utilizing a centrifugal pump for systemic perfusion, what happens if the drive magnet becomes physically decoupled from the pump head housing? A. The pump will immediately double its flow rate. B. The console will show an escalating RPM, but forward blood flow will instantly drop to zero. C. The roller headers will automatically engage to take over. D. The blood will be warmed via mechanical friction. Answer: B. The console will show an escalating RPM, but forward blood flow will instantly drop to zero. Explanation: centrifugal pumps rely on magnetic coupling between the motor in the console chassis and the impeller inside the disposable plastic pump head. If the pump head is misaligned or experiences an extreme pressure spike, the magnetic lock can break, decouple. The motor will spin freely, often showing high RPMs on the display. But the internal impeller stops turning entirely, causing an immediate, catastrophic loss of forward blood flow. What is the role of the bridge line in a dual perfusion CPB setup designed for selective antegrade cerebral perfusion, SACP? A. It shunts blood from the femoral artery to the femoral vein. B. It connects the main systemic arterial line to a dedicated separate roller pump head to allow independent pressure management for brain perfusion. C. It allows the left vent to drain into the aortic root. D. It acts as an overflow channel for the cardiotomy filter. Answer: B. It connects the main systemic arterial line to a dedicated separate roller pump head to allow independent pressure management for brain perfusion. Explanation: SACP requires delivering cold blood directly to the brachiocephalic or carotid arteries at much lower pressures and flows than systemically required, 10 to 12 milliliters per kilogram per minute. A bridge or bypass manifold line isolates a fraction of the oxygenated arterial blood and routes it through a secondary, dedicated pump head, enabling independent control of cerebral perfusion pressures while the rest of the systemic circuit is paused or altered. What safety hazard is introduced if a perfusionist uses an excessively long, redundant length of tubing for the main arterial line setup? A. It causes the blood to clot faster due to lack of motion. B. It increases the required circuit priming volume and elevates resistance, afterload, requiring higher pump work. C. It completely neutralizes the effects of systemic heparinization. D. It causes the roller pump to lose its occlusion setting. Answer: B. It increases the required circuit priming volume and elevates resistance, afterload, requiring higher pump work. Explanation: Circuit design dictates using the shortest possible length of tubing to minimize foreign surface contact and optimize fluid dynamics. Excessively long lines unnecessarily increase the prime volume, aggravating hemodilution. Furthermore, according to the Hagen-Poiseuille law, resistance to fluid flow is directly proportional to the length of the tubing. Longer lines impose a higher resistive afterload on the arterial pump head. During the initiation of CPB, what is the primary structural risk if the venous cannulation site incorporates a loose, poorly secured purse string suture? A. The oxygenator will lose its sweep capability. B. Entrainment of massive room air around the cannula site into the venous line, causing structural air locks in the circuit. C. Direct rupture of the left atrium. D. Instantaneous fouling of the hemoconcentrator. Answer: B. Entrainment of massive room air around the cannula site into the venous line, causing structural air locks in the circuit. Explanation: Gravity or vacuum-assisted venous drainage pulls fluid out of the right atrium or vena cava by creating negative pressure gradients. If the purse string suture around the venous cannulation site is loose, atmospheric room air will easily be drawn, sucked, past the tissue gap into the venous tubing. This can cause massive air entrainment, building up an airlock inside the lines that stalls gravity siphoning completely. Wire level sensors on CPB reservoirs designed with a fail-safe electronic configuration that cuts power to the pump if the sensor becomes physically disconnected from the console. A. To conserve power during prolonged procedures. B. To guarantee that a broken or unplugged sensor defaults to a safe state, stopping the pump, rather than allowing a dry reservoir to go unnoticed. C. To allow the pump to run at higher RPM values safely. D. To prevent the heater-cooler from overheating. Answer: B. To guarantee that a broken or unplugged sensor defaults to a safe state, stopping the pump, rather than allowing a dry reservoir to go unnoticed. Explanation: Fail-safe design dictates that if a critical safety monitoring component fails or loses connection, the system must immediately revert to its most protective state. If the wire to a level sensor is severed or unplugged, a non-fail-safe design might assume volume is normal and keep pumping. A fail-safe loop interprets a broken connection as a critical low-volume state and cuts pump power, preventing an undetected air pumping catastrophe. If an unexpected massive occlusion occurs downstream of the arterial filter in a roller pump-driven circuit without an electronic high-pressure safety cutoff, what will happen? A. The pump will stall due to high resistance. B. Tubing connections will violently rupture or the line will burst off its connectors due to relentless hydrostatic pressure buildup. C. The blood will simply slip past the rollers harmlessly. D. The membrane oxygenator will absorb the excess volume. Answer: B. Tubing connections will violently rupture or the line will burst off its connectors due to relentless hydrostatic pressure buildup. Explanation: Unlike afterload-dependent centrifugal systems, a roller pump is a positive displacement mechanism. It forces a set volume forward with every turn, regardless of downstream resistance. If the line is completely blocked, e.g., a locked clamp or kink, and there is no active electronic pressure switch cutoff to turn off the motor, pressures will surge exponentially until a line connection violently blows apart, resulting in rapid exsanguination into the field. What is the fundamental mechanical purpose of the recirculation prime line during the initial setup of the CPB machine? A. To deliver hyperbaric oxygen directly into the reservoir. B. To allow fluid to cycle rapidly through the oxygenator, heat exchanger, and filter to easily dislodge and displace trapped air bubbles into the reservoir before patient connection. C. To measure the viscosity of the crystalloid prime. D. To test the maximum RPM speed of the centrifugal head. Answer: B. To allow fluid to cycle rapidly through the oxygenator, heat exchanger, and filter to easily dislodge and displace trapped air bubbles into the reservoir before patient connection. Explanation: prior to initiating bypass, every single microbubble within the complex channels of the oxygenator and arterial filter must be eliminated. The recirculation loop links the high-pressure arterial side back to the low-pressure venous reservoir. This allows the perfusionist to run the pump at a high velocity during setup, flushing the priming fluid through the circuit to drive any residual manufacturing air up into the reservoir where it can safely vent to the atmosphere.